We've come to Upper Teesdale for this programme, and in the valley behind me, the river's running over a hard, resistant rock called the Whin Sill. Now, in the 1830s, when this rock was first described, it was called a lava. It was very similar to the lavas found in Northern Ireland along the west coast of Scotland. But later in the 19th century, when the strata around here were mapped in much more detail, and geologists began to look at rocks down the microscope, this view was challenged. Very occasionally, we can come across really coarse-grained varieties of the Whin, and we can actually see in a hand specimen the individual crystals of feldspar and these darker ones, which are pyroxene. But that's very rare. Normally, the sort of stuff that we see looks much more like this. It's medium to fine grained, and even with moderate magnification in the field, all you can tell is that it's a crystalline, igneous rock.
The Whin Sill is exposed across most of northeast England. Its northern edge is marked by an almost continuous series of small, dark cliffs. It stretches from Appleby in Cumbria to the Farne Islands. Nearly 2,000 years ago, the Romans used it as a natural defensive line. They built a good deal of Hadrian's Wall along it. This is Bamborough Castle on the Northumberland coast. Like many of the medieval castles along this coast, it's standing on a pedestal of Whin Sill, because the sill is more resistant to erosion than the surrounding softer sediments. The sill dips gently to the south. A sill is an igneous intrusion. It's formed by a layer of magma moving along the bedding of sedimentary strata and occasionally stepping from one bedding plane to another. The Whin Sill was intruded about 300 million years ago. With erosion, the edge of the sill has been exposed as a thin arcuate strip running across northeast England. Some of the best exposures of the Whin Sill are in quarries to the south of Hadrian's Wall, and in Teesdale it forms a number of waterfalls. High Force is a well-known beauty spot in Upper Teesdale. Here, the River Tees falls over the complete height of the sill, exposing the main body of the intrusion. Near the top of the waterfall are very good examples of vertical columnar jointing. These were caused by contraction inside the cooling layer of magma. The waterfall has also cut down into the sediments below, and at first sight, these look rather like the Whin Sill itself.
Well, I've come down now through several of the sedimentary layers below the Whin, and the rock here is a limestone. But one of the things we expect to find in a limestone is abundant fossils. Down here is a very good example of a compound coral, where each of the individual corallites are perfectly preserved in exactly the position they were when the animal was still alive.
In thin section, you can see some of the beautiful, intricate structures in the skeleton of the animal. The outer wall and the internal subdivisions with crystals of clear calcite filling the spaces in between. Each crack and plane of weakness here is being dissolved slightly faster than its surroundings, a typical feature of limestone weathering. In places, this can result in a kind of pock-marked surface, not found on any other type of rock. It's difficult to get close to the Whin Sill itself at high force, but a little further downstream, you can get up to small outcrops and examine them in detail.
Well, here's a typical exposure of Whin in the gorge below High Force. And this vertical cliff is controlled by the very strong joints in the Whin itself. And there's a very interesting layer here inside the Whin, varying from probably about 10 centimeters through to a good deal more than 20. And within that layer, there are distinct, almost horizontal laminations. And this may be a chunk of sediment that's been broken off and floated up in the wind to this position.
In thin section with the analyzer in, it's an interlocking mosaic of quartz crystals. It was originally a sandstone, but it's been recrystallized as it was heated up to form a quartzite. Many rapids and small gorges have formed where the river has cut into the Huin, and further downstream it's quite easy to find the actual contact between the base of the Huin and the underlying sediment.
Well, here's the Huin again in another part of the Tees, and once more we've got this almost vertical face due to the coaling joints, but here we've got the base of the Huin. It's sitting here on these finely bedded sandstones. And the actual contact is running along here between the Huin above and the baked sandstones below. And the rock from the contact itself is extremely fine-grained. And I've got a sample of it here. On the left is this extremely fine-grained black rock. That's really a basalt, the chilled margin of the Huin. And on the right here is the pale grey baked sandstone.
With the analyzer out, you can see the chilled margin of the Huin where it's in contact with the sediment. The rock is so fine-grained it's almost glassy, with relatively few crystals. But a few centimeters away from the contact, the magma cooled more slowly, and here you find a medium-grained rock called a dolerite, which is typical of most of the Huin sill. And this illustrates a general point about igneous rocks. The slower the cooling rate, the coarser the grain size. The top contact isn't particularly well exposed in Teesdale. The Huin sill is overlain by sandy sediments which have been stripped off, so that the river is now running along its top surface. But here the contact is hidden in the far riverbank. To look at important geological contacts where the rocks are fresh, we often need to go to man-made exposures. This is Ward's Quarry in Northumberland.
We've come to this quarry, which is about 40 miles north of High Force. And here we can see the whole of the Huin in a single exposure. Now, the country rock here are a series of limestones and shales. The limestone is absolutely crammed full of fossils. They're small brachiopods. In life, each shell would have been attached to a similar shell along the hinge line. The other rock type here is a shale, and it too is absolutely full of the same fossils. As the sediment compacted, all the shells became crushed. Now, the bedding here is roughly horizontal, and intruded into these rocks is the main part of the Huin sill. Over here, we've got more of these sedimentary layers, roughly horizontal. But above me, there is the bottom of the sill, and that cuts down right through the sedimentary layers, almost vertically down to this point here. And a junction like this we call a transgressive junction.
The sill cuts through these strata so that you find the same fossiliferous limestone and shales both above and below it.
Well, this is the very top of the Huin. This is the surface which has been cooled against the overlying sediments, and in the broken face here, the Huin can be seen to be extremely fine-grained. And in other places lower down, the Huin, of course, is more coarse-grained. The overlying sediment here is a limestone, and that shows some evidence of baking. And by following the junction round, we can find small places where the two rocks are actually fused together in a single sample. And here's a piece of it. At the center of this sample is a fine white line which represents the actual contact surface where the two rocks are stuck together, and that's the recrystallized limestone, which is now a marble. Below, the black is extremely fine-grained whin, which has chilled against the limestone, and the grey material at the top is the comparatively unaltered limestone.
Less than a centimetre away from the contact, the limestone has hardly been affected at all by the heat of the magma. It's made almost entirely of fossil fragments. But right next to the contact is a thin recrystallized limestone band made of interlocking calcite crystals. This is a marble, and the recrystallization has removed all evidence of the fossils. It's by finding evidence like this baking of the country rock at the top contact of the whin that we can be sure it's an intrusion and not a lava flow. The whin itself is very fine-grained, immediately adjacent to the contact. It's virtually a quenched glass, with just a few feldspar phenocrysts. So in this single specimen, we have three rock types: a limestone that's a mass of fossil fragments, a metamorphic rock, the white marble band, and an igneous rock, the whin itself. Only the eroded edges of the whin sill are exposed at the surface. At Durham, the sill lies nearly 300 metres below the present land surface. It's only 30 metres thick on average, and yet it forms a continuous sheet under most of northeast England. The whin forms only a minute proportion of the strata in this region of the Earth's crust. And if we were able to look at the whole crust in any area, we'd find a variety of structures and rock types. The rocks exposed at the Earth's surface can be classified into igneous, metamorphic, and sedimentary rocks. The rock cycle shows the relationships between these groups. Igneous rocks are formed by the cooling of molten magmas, which have often risen from the mantle into the crust. Sedimentary rocks are composed of the weathered and eroded fragments of older rocks, or the remains of living organisms. And metamorphic rocks are formed by the heating and compression of older sedimentary and igneous rocks. Igneous rocks are molten when they're erupted or intruded into the Earth's crust, but they cool to form an amazing variety of rock textures. This one is a volcanic glass, obsidian. It contains hardly any crystals at all. After it was erupted, it was cooled very quickly, literally frozen, when hot magma came into contact with much colder surroundings. A high proportion of the magmas which reach the Earth's surface are basic in composition, like this basalt. It has a low silica content and a fine-grained texture. But it's cooled just slowly enough to allow crystals to grow, and it's a mass of tiny interlocking crystals of olivine, pyroxene, and feldspar. This texture is typical of many basalt lava flows. Usually they're not very thick, and they have a large surface area for their volume, so they cool fairly quickly, often in just a few months. But sometimes these magmas contain a number of crystals before they're even erupted. As magma rises through the crust beneath the volcano, it travels through a system of fissures and chambers. The magma is stored here, and only occasional pulses reach the surface. Inside the magma chamber, the remaining magma cools slightly, and crystals begin to form and grow. These phenocrysts are completely surrounded by magma, but as time passes they grow larger. Any material erupted to the surface at this stage is a mixture of magma and crystals. After eruption, the remaining magma cools to a fine, even-grained texture. So in this specimen, we can work out that the rock had a two-stage cooling history. The phenocrysts were formed by slow cooling, probably in a magma chamber, and the fine-grained matrix was produced by rapid cooling after eruption. But what happens if the magma is trapped permanently deep inside the crust? Well, here the insulation around the magma chamber is very good, and the cooling rate is very slow. As a result, large crystals can grow, and when the magma completely solidifies, it forms an interlocking system of large crystals. One of the most common rocks formed like this is a gabbro. It's much coarser grained than basalt, even though the magma from which it solidified has the same chemical composition. In thin section, you can see that the gabbro is a coarse-grained, interlocking mass of feldspars and pyroxenes. There are no fine-grained areas, so there was no late-stage rapid cooling. The texture of an igneous rock, in other words, the size and shape of its minerals, depends mainly on its cooling history. Igneous rocks which form deep inside the Earth's crust are often later exposed at the surface by uplift and erosion. These gabbros on the west coast of Scotland have been exposed by considerable erosion. Massive amounts of material have been removed from above these outcrops by glaciers and rivers. And this brings us to the next major category of rocks in the rock cycle.
We can look at the texture of sedimentary rocks in both hand specimen and thin section to find out something about the environment of deposition in which the original sediment was laid down, and also sometimes to find out about the processes that have gone on to transform that original sediment into a hard sedimentary rock. This is a coarse-grained sedimentary rock. It's a conglomerate. It's made up of large pebbles of other rock types, chiefly pebbles of quartzite, and the whole thing is cemented together in a hard matrix of finer material.
A conglomerate like that was probably deposited along a seashore, where the energy of the water environment was very high. The currents here are too powerful to allow smaller particles of sand and mud to be deposited. A little further away from the turbulent inshore environments, finer particles can be deposited on the seafloor. It's possible to find sandbanks like these fairly close to the shore, but most of the material eroded off the land is deposited in much deeper water. Moving away from the coastline, the seafloor naturally gets deeper, and the current velocities get less. As the water slows down, the sandy particles are deposited first. And further out to sea, in quiet, deep water, the very fine mud particles settle out. With time, the sediments become thicker, and as more and more material is deposited on top of them, they become compacted and hardened. Most of the water between the grains is squeezed out.
Now, sometimes it's possible to find several different textures within a single specimen. This layer here is rather like the conglomerate, formed of rounded fragments, largely of quartz. But below it, there's a much finer grained layer, which is formed of individual mineral grains, chiefly of quartz and feldspar. It's a sandstone, and was obviously laid down under much quieter conditions than the conglomeratic layer above. Now, although we can find out a certain amount from the texture of specimens like this in hand specimen, we can see very much more if we put a thin section of such a rock under the microscope. I've got a polarizing microscope here, which has got a camera on top linked up to a TV monitor so that you can see what's going on. And I think you can probably see very clearly the rounded fragmental grains of quartz that have had their corners taken off as the sediment jostled together during transport. And between these are clear areas of cement. Now, if I put the analyzer in, the high interference colors, the bright interference colors of the cement tell me it's the mineral calcite. And it's this calcite which has been laid down by waters percolating through the sand that result in the hard sedimentary rock. Now, there are much finer grained sediments than sandstones, and I've got a sample here. It's a shale. It's largely formed of clay minerals which have been laid down in more or less horizontal layers in quieter and probably much deeper water than the sandstone. And it still preserves this finely laminated texture in the final rock. Any organic material falling into the soft mud from which this rock is formed is likely to be beautifully preserved. There's a nice example here of a trilobite that was squashed flat as the mud compacted.
Any rocks, however they were formed, may eventually get buried deep beneath the surface. Here they experience high temperatures and pressures, and they become deformed. Finally, they recrystallize, and the different combinations of conditions deep in the Earth's crust can form a wide variety of metamorphic rocks. This is one of the simplest and most common metamorphic rocks, a slate, which started out as a shale. There's been a certain amount of recrystallization, but it's still a fine-grained homogeneous rock. The sides of this specimen are bounded by cleavage planes, which developed when the rock was metamorphosed. And you can still see the original sedimentary layering running at an angle of about 30 degrees to the cleavage. These sedimentary layers were horizontal in the original shale. As they were compressed, they became folded, and eventually a series of cleavages developed parallel to the axial plane of these folds across the original sedimentary layering.
Now we can easily tell that the slaty cleavage has developed after the sedimentary laminations by looking at a thin section. Here are the laminations of the original bedding, and cutting across them, these black lines are the beginnings of slaty cleavage, and they're formed by the growth of minute mica crystals that develop during metamorphism at right angles to the direction of maximum pressure. Now, as conditions of metamorphism become more intense, these new textures become much more obvious. This is a mica schist, and here the bulk of the rock is formed of quite large crystals of mica, and they're all aligned at right angles to the direction of compression during metamorphism to give us a direction of schistosity. And if we look across here, we see another very characteristic feature of metamorphic rocks. This is a large garnet crystal. It's got very clean, well-formed crystal faces, and the mica crystals appear to bend around the garnet crystal. Garnet is very easy to recognize in metamorphic rocks because it's an isotropic mineral. So with the analyzer in, it's dark. And if we take the analyzer out, it seemed to be high relief and pale in color. Now over here, we've got a sample of a garnet mica schist, but here the garnet crystals are more than ½ centimeter in size. But the important thing about this rock is it's still perfectly homogeneous. It's still a schist. Now, as conditions of metamorphism get more intense, we get the development of bands with the so-called gneisses. And here's a good example. Individual minerals segregate into dark and lighter bands. And the important thing to remember is that metamorphic banding has got nothing whatsoever to do with the original sedimentary layering. We can get a texture like this developed even from an igneous rock. And finally, when conditions get even more severe, any rock may melt. And then, of course, all traces of metamorphic texture will be lost. And from the magma, a new rock will form, which, if it cools slowly deep in the crust, will develop a typical igneous interlocking texture, just like this granite.